4. And I request Krishna Nandiwada, who is the head of our department, to introduce the speaker.
All right. I mean, it's an absolute pleasure introducing Akshay Utture. Uh, I had great time when he was here. He was working with me for a short period of time. So at IIT Madras, he did his BTech dual degree, right? And after that, so he not only worked with me, but he also happened to go and work with my guide for his PhD. And after defending his thesis, currently he joined uh, the Uber's programming systems group, where again it so happens a bunch of my close friends were there, and I think are still there. And I'm sure he's doing great work. So today we will have the opportunity of hearing what all Akshay has been doing and is planning to do. Akshay, welcome. We are
Yeah,
proud of you.
thank you for that introduction. I am quite excited to be back here giving this talk at IIT Madras. So I'll just start by sharing my screen. Um, okay, yeah, is my screen visible?
Yeah, it's coming up.
Okay,
Yeah,
perfect.
go ahead. Yeah.
Thank you. So yeah, my talk is going to be about static analysis and automated repair for Java resource leaks. So I'm currently working at Uber, but most of the work in this presentation is from my PhD at UCLA. And uh, do stop me at any point if you have uh, any questions, and we can take the questions as I go along. So yeah, let's get into it if you're all ready. Yeah, so let's start off by taking a look at what are resource leaks. So resources such as files, sockets, and database connections can leak and be the cause of bugs that can cause severe failures. And when the OS runs out of a particular leaked resource, the program is going to crash. So here's an example of a leak on the right. We have a function foo with this file reader object, and the file reader object never gets closed because there's no fr.close call. And so this resource is going to leak. And the interesting thing about resource leaks is that they are elusive. So tests usually do not exhaust all of the resources of a particular type. So these leaks are not going to show up during testing. They unfortunately will only show up during production and cause a crash, and outages can be very expensive for a lot of companies. So the only current good way to detect resource leaks is through static analysis tools. So they can catch these errors without actually running the program. And there are actually many open source Java resource leak detectors out there. But empirical studies show that developers often want fix suggestions along with just warnings about issues. So the problem statement that we're trying to solve now is, can we automatically fix resource leaks for Java? So before we start, I'll give like a really quick background on static analysis so that we're all on the same page. So today's software code bases have millions and sometimes even billions of lines of code, and we need automated tooling to help maintain such huge software. So one of these techniques is, one of these automated tools is static analysis, and it can analyze the source code of a program without running it and automatically find vulnerabilities, errors, and opportunities for optimization. And these are sort of better than testing in many ways. One of the ways is it does not really rely on inputs. And secondly, it can catch problems like the resource leaks that we saw or security vulnerabilities, which are things that actually don't show up during regular testing. So there are a few applications of static analysis. So it can catch security vulnerabilities like SQL injection. It can prevent crash-causing errors like null pointers and resource leaks. It can be used to optimize the program like using constant propagation. But today we'll mostly focus on the resource leaks part of it. So one important concept in static analysis is data flow analysis. And here's the really quick overview of it. So uh, the data flow analysis tries to represent the flow of certain data values through the program. So a really simple example that probably everyone can relate to is a null point analysis. So we want to find out which variables in our program can potentially be null, because if you dereference them, they can cause a null pointer exception. So in the program on the left, let's say we have the access of the field x.f. If x is null, then x.f is going to throw a null pointer exception. So we want to know whether the different variables in our program could potentially be null. So the first step is we pick an abstract domain. So all the variables can actually take several different values, but we're basically interested in whether they're null or not null. So we're going to represent only these two values in the program. And the next step is we construct a data flow graph. So in this case, we see that so the first statement in the function here is x is equal to new a. So x gets a not null value. The next statement is y is equal to null. So y gets a null value. The third statement is x is equal to z is equal to x dot f. So z gets its value from a dot f, and a dot f will probably get its value from the constructor, which is not shown here. And finally, the return value gets its value from y. So now that we've built this data flow graph, the next step is going to be to propagate all the data values. So if we propagate all the values in this graph, we'll see that x ends up getting not null, y ends up getting null, and the return value also ends up getting null. So this propagation is going to happen through some kind of reachability analysis. And of course, there's a lot more to data flow analysis, but this was just a quick recap. The next quick concept that I'd like to look at is demand-driven analysis. So this is a slight modification of a data flow analysis where we'll only compute the data flow graph needed to answer a single query. And this technique is super fast for single queries. So let's say we want to answer the query, can x.f throw a null pointer error? Then for a demand-driven analysis, we only construct the part of the data flow graph which is necessary to answer this question. And we just need the node x and the value not null that it gets its value from. And based on this, we'll compute the result x is equal to not null, and we can answer the query that we were looking for. So the demand-driven analysis analyzes only that part of the program which is necessary to answer a single query. I could take any questions now if we have any questions up to this point. If not, I can move on. So now that we understand a little bit about static analysis, let's get back to our problem statement, which is trying to auto fix resource leaks. And let's look at some existing options that we have for this. So there's two sort of kinds of tools we can use. The first option is general purpose repair tools. So there are some repair tools that that work on any kinds of errors. And the second is footpatch. So footpatch is this semi-specialized repair tool that works on heap errors, which include resource leaks. But there's no specialized tool for resource leaks so far. So let's try applying these options. So the way a general purpose repair tool works, in short, is that it generates some candidate patches using machine learning or search or a variety of other techniques. And after generating this potential candidate patch, it will validate the patch by running tests. So basically, at least one test which was previously failing should pass after applying this candidate patch. And if all the tests pass, then the candidate patch works. But we can't apply this kind of paradigm to resource leaks because remember that resource leaks are not visible in unit tests. So let's look at the other option, which is foot patch. It's this semi-specialized repair tool. It works on a few errors, including resource leaks, null pointers, memory leaks, and how it gets around the problem of that general purpose tools face is that it relies on static analysis to verify patch correctness. So there's a resource leak static analysis which points out a leak. Then Footpatch also generates a few candidate patches and it reruns the resource leak static analysis and ensures that the leak has disappeared. So instead of using tests, it can use the resource leak static analysis to verify the correctness of the fix. And the issue is that it pays for its generality with a little bit of quality. It only generates fixes for 6% of the leaks, out of which only 27% are correct. So let's take an attempt to try and fix a resource leak. But before that, let's take an example of a resource leak and let's see how we might fix it by hand. So here is a resource leak on the right. So let's take a look at the code first. So we have a function foo. It has a file reader object created on line 3, and this fr variable gets passed into the method bar on line 4, but this variable fr is also read from on line 5. Next, let's look at the method bar, and in this method bar it takes a parameter as the file reader f, and on line 11 it creates a new buffered reader object. And it reads from this buffered reader on line 12, and that's about it. It never gets closed. So if you run the infer static analysis tool, it'll report a leak on line 11. So through this example, we're going to actually look at 4 things. We'll start off with this important concept called resource aliasing. The second is we look at how Footpatch, which is the baseline tool, how it might suggest a fix. Then we look at what are the steps to generate a correct fix by hand. And then we look at the fix generated by RL Fixer. So in this example, the buffer reader takes a parameter f, which is a file reader, as input on line 11. And what ends up happening is that the buffer reader here is a wrapper for the file reader object. And it provides some buffering functionality to the file reader. So in this case, R and F are actually resource aliases. And what this means is that they point to different Java objects, but they use the same underlying OS resource. So any operation on a resource also applies to its aliases. So remember that resource aliasing is sort of similar to pointer aliasing, but it's not exactly the same because, as I pointed out before, there are actually 2 different Java objects. So there's 2 different values on the heap, the file reader and buffered reader, but they are still using the same underlying OS resource. And it's important to identify these resource aliases if we're going to make a correct fix. Now let's look at Footpatch's fix. So Actually, for this particular example, footpatch is unable to generate a fixed candidate, but the way it works is it applies a fix at the location given by infers warning. So infers warning is that the resource of type buffer reader at line 11 is not released after line 12. So what footpatch would have done is whatever fix code it came up with, it would have applied it at line 12. And you can see what the issue is over here is that closing the resource buffer reader inside the method bar is actually an incorrect fix because there is this alias f which is alive even after bar completes. So notice that on line 5 we're reading this variable fr.read, and remember that the file reader and the buffer reader are actually resource aliases. So if we close the buffer reader in the bar method, we are going to get a use after close error on line 5.
Akshay, one question here.
Yeah.
This is there a class hierarchy relationship between file reader and buffer reader?
No, absolutely not. They are completely unrelated in the class hierarchy.
But then this aliasing, resource aliasing relationship, isn't it application dependent? In the
Yes,
sense,
it is.
yeah. So in this case, it might be these are standard Java classes, so that might be okay. But in general, it might be an application dependent. I might have wrappers over these which are user defined, and then identifying these resource aliases will be possible, or what is your take on?
That's a great question. Yeah. So it depends. There are actually many ways to define wrappers, but there's usually one particular pattern that is usually used, and we can use that to capture most resource wrappers. And I
I
will
see.
get to that analysis very soon.
Sure, thanks.
Yeah.
Akshay,
Yes.
on a related note, can we assume that these wrappers were given as inputs as well, along with the program? The developer could say, "Hey, here are my resource wrappers."
Sure, they could do that. They would have to sort of annotate all pairs of wrappers in their code. But
Yeah, in some way, yeah. What way they can give is, I guess, to can be, yeah.
yeah, but again, asking developers to annotate this is often ends up being a little bit difficult in practice. But I'll show that there's a way to capture most of these uh, wrapper relationships using static analysis.
Okay.
Yeah. Okay, so what would be the steps to generate a correct fix in this case? And yeah, so the first thing we need to identify is whether the leaked resource actually escapes the context of the method in which it's defined. So in this case, we have to answer whether the buffered reader or any of its aliases actually is accessible outside the method bar. So in this case, yes, the file reader is accessible outside the method bar. And so we can track its backward slice to this line 3 over here. So by backward slice, I mean by analyzing all the statements which are relevant to that particular statement that we're looking at. So we want to know where this file reader gets its value from. We can trace it backwards to line 3 where it gets its where fr gets its value from new file reader. And then we can repeat this analysis. We can ask this question again: does the file reader escape the context of foo? It actually doesn't. So in this case, we can actually close this file reader resource inside foo safely. And on the right, we have the fix generated by RL fixer. So the repair specification that our tool RL fixer is going to get is to close the leak without modifying the program semantics. And we need this nested try finally block to actually preserve the control flow exactly during exceptions. So what RL Fixer is going to do is it's basically going to run the 3 steps that we saw on the previous slide, but in an automated fashion. So it's going to do that using a new kind of analysis called a resource escape analysis, which tracks how a resource escapes its method. And then we're going to use that analysis results to pick the right repair template, and using the right repair template, we're going to generate the fix, which is shown on the right. So we saw that RL Fixer could fix that resource leak, but an interesting thing is that there are some resource leaks that actually may be infeasible or too hard to fix. So here is an example of one. So on the right, we have a class B, which has a field writer W and a function foo. And down below, we have some code which says x is equal to new B and x.foo of a new file writer. So you can see that the file writer resource actually escapes to the field writer W. So this means that this file writer is accessible as long as X is alive. So we can really only close the file writer when X is to be deallocated. So fixing this leak is going to be at least as hard as compile time object deallocation. That is static garbage collection, knowing when X can be garbage collected. And Java has a dynamic garbage collector because it's a well-known problem that static garbage collection, at least for Java, is a very hard problem. And there are a few other kinds of resource leaks, like those that escape to arrays or static fields, which are also very hard to fix because, again, for them, it's hard to know uh, to when the resource sort of stops being live. So,
Sir, I have a doubt in the
yeah, go
previous
ahead.
slide. You were mentioning that the resource, like the fix is infeasible for the tool to be found. But why can't the tool have this approach of having like destructors for objects when they are automatically like being garbage collected? Like trigger all the OS resources being used to be destructed on.
Right.
I
So Java actually doesn't have the concept of destructors. And the thing, yeah, Java doesn't have the concept of, so all these resources will end up getting collected when the program terminates. And if you have like a long running program, like let's say a web server, which could be running for days or weeks even, you will run out of that resource.
okay, yeah, sockets will be like, out of
Yes, you can run out of sockets, you can run out of file handles. All those are limited resources
okay.
on
So isn't it like a better option to like have like better like improve the programming language constructs to like manage the resource leaks, and that's why we have like new languages coming up.
Sure. So that's actually a great point. And like one possible thought that might come up is like, if we can do garbage collection for memory, why can't we also do garbage collection for resources? And the thing about this problem is that so memory is completely in the control of the Java runtime. So it knows exactly what all objects you've created and it can garbage collect it. But the resources are actually at the level of the OS. So the Java runtime sort of doesn't have a full picture of uh, what resources are actually out there, and like it can't perfectly tell which pairs of resources are actually aliases. So that's why it's hard for the Java runtime to garbage collect it. And I think I'm not sure how much programming languages will have to be. I'm not sure what it would take to sort of have the language runtime get this kind of information from the OS potentially, but that's what makes this hard.
Yeah, that's fine.
Yeah. And another thing is, so sometimes in sort of like, let's say Android apps or something, you do have a destructor that's called when an Android app page is closed, uh, for example. But sometimes it's even too late by the time the destructor gets called. But and in general in Java we don't have destructors. Yeah. So if there are no questions, I can move on to the next section, which is the approach taken by RL Fixer. So we start off with the program source that's fed to some black box resource leak detector. And there's already quite a few good ones out there. And they are going to spit out a set of warnings. And these warnings are going to be fed to RL Fixer, which basically has 4 components. The first component is simply going to parse warnings in a normalized format. The second is the resource alias identification. Remember that we spoke about how the file reader, and buffer reader were resource aliases. So this component is going to identify those. Then the next component is the resource escape analysis, which, as I said, will find out what constructs it'll tell you how a resource can escape the context of its method. And then finally, we're going to apply some repair templates to actually make the fix. And at that point, we're either going to declare a resource as infeasible to fix or give out the actual fix. So let's start off with looking a little deeper at the resource alias identification. So the definition we're going to use is that X and Y are resource aliases if X is a wrapper for Y or Y is a wrapper for X. And then resource W constructed with the constructor CW is a wrapper for a resource R if these 3 conditions are met. And we can see these 3 conditions in the light of the example on the right. So we have the class wrapper type, which has a field out, and it has a constructor for wrapper type and a close method. And somewhere further down, we have some code that calls that has these 2 variables X and Y. X is equal to new resource type, Y is equal to new wrapper type, and we're trying to answer if Y is a wrapper for X. So we say that the resource, so I'll go over the definition of resource wrapper now. So resource W constructed with the constructor CW is a wrapper for resource R if R is passed as a parameter to CW. So in this case, X gets passed as a parameter to the wrapper type constructor. So we've met the first condition. The second condition is that R be a must alias with a field of W at the end of CW. So aliasing refers to pointer aliasing. So if 2 pointers point to the same value, they're said to be aliases. And alias information can be computed using a pointer alias analysis, which is a very standard and well-known static analysis. So the second condition is that R must alias with a field of W at the end of the constructor. So if we look at the wrapper type constructor, we see that the field out is assigned to W, and so the second condition is also met. And finally, the must alias field should get closed in the close function of the wrapper. So in this method close, we see that the field out also gets closed. So basically, to sum up, what's happening here is that whenever you call close on a wrapper type, it also closes its underlying resource type. And this is sort of
Akshay?
not, yeah, yes.
I had a quick question. So is this information flow insensitive?
Yes, this is okay. So technically,
Is it flow and context insensitive?
it is context insensitive. Yes.
In such a case, if
Step
it is flow and context insensitive, then how is it that so you will only get, are you computing may information or must information?
So you should compute must information. So actually, step B will require a flow sensitive analysis.
Okay. And
actually, in fact, sorry, step C also may require a flow sensitive analysis. Yes.
Okay. And you perform flow sensitive analysis for BC and so do you do fully flow sensitive analysis or?
Yes, just for those methods. Though it's an intra-procedural flow sensitive analysis, so it's within the close method and within the constructor. So
I see.
Yes. So actually, right. So actually, anyways, this definition is sort of not 100% perfect. I would say like 95 to 98% of all resource wrappers can be captured with this pattern. But as Rupesh sir pointed out, there are other ways of creating a wrapper, and this pattern may not capture those, but this works in most cases.
Okay. I mean, the issue for me was that you are closing all of them. So since you are saying you will close all of them, all the aliases, so that's why you are looking at must aliases. And what if if condition 1 out equal to W1, else out equal to W2, then you will not identify resource leaks in them. Is that right?
So we're doing resource leak fixing. So we won't be able to say that X is a resource alias of Y for sure.
Okay.
It may be a resource. So basically, when
so you'll report it as a possible resource leak.
Yes.
Okay.
So actually, a slightly interesting thing is for the resource leak fixing problem, both false positives and false negatives can generate incorrect fixes. So it's actually tricky as to what is the right thing to do over here. So if you miss a pair of aliases, like we saw in the previous example over here, if you missed the alias over here, you would produce an incorrect fix. But if you assume two things are aliases, even though they're not, then you may close one of them and assume that the other is closed, but the other will remain a leak. So both false positives and false negatives are both dangerous in this case.
Okay.
So you can also think of an analysis where you do like a may alias one for steps B and C, and it 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 may work out okay.
Mhm.
It's a trade-off at the end of the day. So the next step of RL fixer is this resource escape analysis. So I won't get into too much details, but this resource escape analysis is a new demand-driven static analysis, basically a data flow analysis, and it's used to compute a resource's escape types. So it can be demand driven because remember that we are going back to this page, we're actually getting the warnings from the resource leak detector. So the resource leak detector has done this whole program analysis and pointed out maybe 4 or 5 locations where we have resource leaks. And we can do a demand driven analysis for just those 4 or 5 resource leaks and be super fast. And what this escape analysis is going to do is going to compute a resource's escape types. So the escape types are going to be the kind of program constructs that a resource escapes to. And there's going to be 2 uses of this. First is it's going to help us identify the infeasible to fix leaks. And then it's going to help us generate repair code. So here is a list of it's an exhaustive list of escape types for the resource escape analysis. So these are the 5 ways in which a resource can escape the context of its method. So if the resource object aliases with either an instance field or a static field, we say that it has a field escape. If it aliases with an element in an array or data structure, we say that it has a data structure escape. If it gets returned by the method it is created in, we say that it has a return escape. If it aliases with a formal parameter of the method in which it's created in, much like in the example that we saw, we say that it is a parameter escape. And finally, if it's passed as an argument to an invoke statement, then we say it has an invoke escape.
Actually, sorry.
And
What's the difference between? So where do you store anything in a data structure which is not a field or an array?
so let's say you store it in an array or a hash map.
But that's not part of a field, is it?
That's actually I don't consider it, but you could imagine that a lot of data structures do have a field. They implement this using a field. But usually we don't want to end up actually, that's a good question. Let me think about it. That's a good question. So maybe, as you pointed out, a lot of data structures will end up being implemented with having like an array as a field, and then they'll end up being field escapes. Uh, Splitting it this way has one advantage, which is that we don't have to analyze the data structure class.
So you are not analyzing the libraries, is that right then? You are kind of having that hash table, array list, fixed data structures, is it?
Yes, pretty much.
Okay. Second question was related to this parameter escape and invoke escape. How are the two different?
So in this case, just going back to the example. So for the method bar, we can say that the buffered reader has a parameter escape because the file reader escapes via the parameter. Whereas, let's say we're analyzing the file reader, we'll say that the file reader has an invoke escape on line 4. And the need to differentiate these two is that if you have an invoke escape, you can still close the resource at the end of that method. But if you have a parameter escape, you probably cannot close the resource by the end of that method.
Also, this is useful for fixing the resource leak. Okay.
Exactly.
Okay. Thank you.
Yeah. So if we have field escapes and data structure escapes, we're going to declare them as infeasible to fix. And the other three escape types will help us generate the correct fix. So why field escapes and data structure escapes are hard are we saw an example of one of them before. At least for instance field, it's at least as hard as compile time object deallocation. And in general, for fields and data structures, it sort of reduces to some hard problem, some known hard problem. So we've done the resource escape analysis. We know exactly to what kind of constructs the resource can escape. And finally, we can apply the repair template. And when we're applying the repair template, we'll declare it, we'll either get the fix or we'll declare it as infeasible to fix. So this is the decision tree, which is hand crafted, and it's used to generate the repair code. So if it's a data structure escape or a field escape, it's infeasible to fix. And so that the top three nodes in this decision tree are based on the escape types, and the bottom three nodes are based on some source code structure, and they result in 3 repair templates. And applying the repair templates in the appropriate scenario will give you the correct fix. So moving on to the experimental results. So for the data set, we use 5 existing leak detectors and ran them on this NGR1 data set, which is simply a data set of 287 Java programs. So you see that each of the leak detectors is different. It catches a different number of warnings, but they roughly have 2,205 unique leaks, and we have 1 leak per 1,300 lines of code. So this is a somewhat common problem. So for the results, the first number we're interested in is what is the fixable rate. So out of the total number of warnings, how many warnings, what are the number of warnings that we could suggest a fix for? And we have the numbers for each tool. The average is the portion in green is the fixable rate. So on average, we can fix 66% of resource leaks in this way. And around 9% of the leaks were unfixed because of escaping to a data structure, and 20% were unfixed because they escaped to a field. And there are a few corner cases why the last 5% couldn't be fixed.
Akshay, one question here.
Yes.
Is NGR dataset designed to contain these resource leaks? Are these all published that these many resource leaks exist?
So these are actually just programs taken from GitHub. And the nice thing about them is that they run with a large variety of tools. So these 5 resource leak tools just run off the shelf on them. Usually what happens with data sets is getting static analysis tools to run on them, like on spec or so, is a bit of a pain. So that's why we pick that's why we pick the NGR1 dataset.
But these 2205 unique leaks, these are reported in literature. It's not reported by the dataset.
No, it's these are 2205 leaks reported by these 5 existing popular resource leak detection tools.
I see. I see. Okay, sure. Got it.
So there could be a few false positives among them potentially.
That's right. Sure. Got it. And some of them might not have been found out yet.
Yes, exactly. So it could also miss leaks and have false positives.
Got it.
So it's an interesting question as to what would happen if you tried to fix a false positive leak. But for the proportion of leaks that we attempted to fix, we found no false positives in a sample of 150 leaks.
That is actually impressive that you did not find false positive.
But also it's the caveat there is that we're sort of going for the easier leaks. So the harder leaks, like the ones which escape to fields and uh, data structures, those are the ones which are much more likely to have false positives.
I see. I see. Sure. Thanks.
Yeah. So the next number that we're interested in is the fixed correctness. So out of all the warnings with the fixed suggestion, how many were correct? And we computed this by taking a sample of 150 fixes, around 30 per tool, and then doing two things. One is we manually verified the fix by 3 volunteers per fix, and we reran the resource leak detector also to ensure that the leak disappears. So on average, 95% of the fixes were correct. And the last 5% of fixes were incorrect because we couldn't perfectly identify all resource aliases. And second, there are this technique works well when there is only one resource leak in a block of code, but if the same block of code releases if the same block of code has multiple resource leaks, then the tool doesn't give the right output. So the other thing, we also want to compare with the baseline, which is foot patch. So on the NJR benchmarks, foot patch fixes 15% of the gets a fixable rate of 15%, out of which 50% are correct. Whereas RL Fixer attempts 65% of the errors, out of which 99% are correct. And on APK tool, which is the resource leak benchmark from the footpatch paper, it's the only resource leak benchmark for Java, and footpatch gets a fixable rate of 8%, whereas RL Fixer gets 92%, and the fixed correctness is 100% for both of them. So
Akshay, can you comment on this NGR versus APK? Why there is large fixable rate?
So the thing is, APK tool is just okay. So the RL fixer is actually a semi-specialized tool. So it works on Java and C, and it works on resource leaks, memory leaks, and null pointer errors. So they have benchmarks across all of these, and APK tool is actually the only Java resource leak benchmark. So it's just a single program. And what you see, this 8% fixable rate is actually just a single leak. So
Yes. Sure.
out of the 13 leaks, it fixed just one of them and it got it right. So
And there was, I mean, does RL Fixer cover all the ones that are identified by foot patch?
uh, yes, it does. So the
Okay.
foot patch fixes are a subset of the RL fixer ones.
Okay. Thanks.
Right. So the takeaway here is that foot patch is much more general in the kind of things it can fix, but it pays for its generality with a lower fixable rate and a lower fixed correctness. And the last thing we want to know is what is the repair time? How quickly could we come up with a fix? So here we have for each tool the time it took for the leak detector to run. And on average, the time to generate a fix is 14 seconds. And we also have a split up of the fix time. So RL Fixer is implemented on top of this analysis framework called Vala. And Vala takes time to be set up, including things like call graph construction, which is computing the set of potential method calls in the program and other kinds of things that are needed. And that takes 13 seconds, whereas the RL Fixer portion just takes 1 second because it is demand driven, so it runs super fast. So one question that has come up recently, and I'm sure people are interested in, is can we auto-fix resource leaks with LLMs? And the short answer is that for simple cases, yes. For complex cases, probably not. So what would be a simple case? So if a resource is local to a method, then we can simply feed the LLM with the method and the leak warning, and maybe optionally give some fixed examples, and it'll usually get it correct. But what happens, we may need like a resource escape analysis or some other analysis to decide if the leak is local. For a complex case where the resource escapes the method and it's accessible across multiple methods, it usually doesn't get it right because it needs to understand data flow to generate a correct fix. So the example that we saw, we actually ran this through an LLM. So we fed the LLM these two functions, and we also gave the leak warning. And what the LLM ended up doing was it ended up fixing it in the method bar, which, as we've seen before, is an incorrect fix because it will give a use after close error. So in general, so this applies to RL Fixer, but in general, there are like some advantages and disadvantages of using LLM. So one really nice thing is that you don't need a dedicated tool for each type of error. So it took me a lot of time to sort of design this specialized resource leak analysis and these handwrite these templates. But for an LLM, you just give it the warning and the code, and it can potentially come up with a fix. And it also works across languages and versions. So if you built an LLM-based fixing tool, you wouldn't have to do too much work to get it to work on other languages. And finally, the third thing, which I think is like actually really huge, is that an LLM can potentially be applied to fix errors that are probably never going to be fixed by traditional tools. So actually, the project that I'm working on at Uber is generating fixes for code review comments. Now, the thing is, in the code review comment, the specification for what, so for those of you who are unfamiliar with code review, when it's like when you upload some code on GitHub, there'll usually be a code review where another author on the code base will ask you to make some changes, and then you make those changes, and only then your code gets accepted. So in the code review, there are requests for changes in the form of human text, and the human text can often be ambiguous, and it's very free form. So it's unlikely that we're going to be able to get traditional tools to fix that, and LLMs have a decent chance at them. But there are some disadvantages with LLMs. So one is they have probabilistic outputs, so you have less control over what it's going to produce. And in fact, even for the same input, there can be a different output every time you call it because it's probabilistic. And it's also prone to errors and hallucinations. So that makes it unreliable. And the problem is that users dislike incorrect fixes. So if you want to use an LLM, you have to be able to filter out these incorrect fixes. And of course, it's very hard to test and debug because you're going to get a different output every time. And of course, it's also expensive in terms of calling the OpenAI API or running on a GPU, and it's also slow. It can take a few seconds per fix. And yeah, so to conclude, Uh, so resource leaks are an important bug type that need better support for automated fix suggestions. And our tool RL Fixer uses a new resource escape static analysis to identify the leaks that are infeasible to fix. And for the feasible one, it helps pick the correct fix template. And the result is that on 5 Java resource leak detectors, RL Fixer can automatically fix 66% of the warnings and in just 14 seconds per benchmark. And out of this, 95% of the fixes are correct. And yeah, that's about it for my talk. Thank you for listening. And I forgot, I should definitely also mention that I actually learned static analysis for the first time in Rupesh sir's class. And then I also learned a lot more from Krishna sir when I worked with him on my dual degree project. So I really have a lot to thank both of them for. And yeah, I can take more questions too at this point.
Yeah, one small question about the LLM. So let's say that, I mean, do you have some thought on approximately how much percentage of these resource leaks can be identified and fixed by LLMs?
Yeah, so actually, I am working uh, on this problem as well. And my rough estimate is that around 40% of the 40 to 50% of the warnings may be fixable.
I see.
40%, yeah.
I see. So
So
good to know that we are still in the job.
yes.
Okay, sure. Yeah,
But
any
one thing is that so we'll still need a lot of work to get this to work well, because if you just throw all 100% of warnings to the LLM, you're going to get 40% correct warnings and but 60% incorrect warnings. And that, and a developer is not going to like a tool with so many incorrect warnings. So if we really have to use an LLM for this, we have to figure out how to filter out those 60% of warnings that it can't suggest a correct fix for.
That's right. Maybe we need a program analysis after LLM has done its job.
Yes. Or an analysis before to decide if this leak is, simple. So if it's sort of
Right.
localized to the method, it's more likely to get it right.
Yeah, that makes sense. Right. Anybody in the audience has any questions? Please feel free.
I have a small question.
Yeah.
So, when you categorize the resource leaks into those 5 categories, right? Like 2 of them you said are like infeasible. So, how
Right.
accurate is that? How accurately do you classify this? Do you get errors while classifying these? For example, do you classify an invoke escape as a field escape by mistake? Does that happen in your?
So this pretty much never happens. So what what static analysis tools generally do is, okay, so one quick clarification is that the same resource can have multiple escape types. So if a resource escapes via an invoke, it could also escape to a field. Uh, but coming back to your question about what if we don't compute this accurately. So what static analysis tools do when they cannot perfectly compute runtime information is that they over approximate. So it may be possible that something doesn't escape to a field, but by over approximate, I mean that uh, it considers uh, all possibilities. It considers what can happen across all possible program executions, but it may also include effects of some impossible executions. But it'll never sort of miss the uh, the potential behaviors from any execution. So if you have like an if-else branch, and it'll assume that both branches can be taken, for example. So in that case, something may not be a field escape, but we may classify it as a field escape, in which case we won't suggest a fix. So yes, we may miss out on some fixing, some opportunities to generate a fix, but usually we won't attempt an infeasible to fix leak.
Okay, thank you.
Yeah.
Any other questions, anyone? All right, then let me thank Akshay for a wonderful talk and for sparing his time. Um, uh, Towards the end, I would also like to mention an important trivia about Akshay. He is actually the student member who has single-handedly coded the elective allocation tool, which we call as SEAT. The user documentation as well as the code documentation was very professionally done by Akshay and some other members. And that was very useful in transitioning, in fact, the seat software from the team all the way to workflow. So currently it gets managed by workflow, but the code used is still Akshay's underneath. And this trivia was provided by Meghna. She could not join today, but she wants to mention this and thank Akshay for his useful contributions to IIT Madras. Thanks, Akshay.
Yes. Thank you. Thank you so much for having me. This was so great. And yeah, I'd also like to mention there were a lot of other people on the SEAT team as well, including Meghna ma'am. And it was great working on that project. And I'm very glad that it's still being used. And do reach out to me anytime if you want to talk more about my research or about today's presentation. My email is akshay.utture@gmail.com, or you can also look me up on Google Scholar or my website. So I'd be happy to chat more about any of this stuff. So do reach out.
All right. Thanks a lot, Akshay. Thank you everyone for joining. See you. Have a nice day.